I have to say it's so nice to be back on the IP Showcase stage since, what, 3 years almost? Amazing, amazing. It's good to see so many friendly faces. So look, my name is Ievgen. This is Pavlo. You'll see him in a moment. For those watching us on YouTube, we are with the European Broadcasting Union, and the topic of the presentation is basically the possibility of using PTP for media production over 5G. And the question would be like, why would you do that? So that's what we'll tell you. So this exercise was done as part of the European project called 5G Records, which EBU is part of. It's a consortium of different media organizations, including some of the telecom providers, some industry vendors, some media companies like the BBC, like the RAI, the EBU as well. And in particular, we've done that as part of the so-called use case 2, which is the mobile wireless studio. So you can imagine like having an OB van, and then on top of the OB van, you have your 5G base station, and this base station is used to get your wireless cameras in the field. So essentially like replacing your traditional RF cameras that are not as spectrum efficient as 5G cameras, potentially. And there was some of the assumptions made in the project. One of the assumptions was that the local studio is actually running ST2110. ST2110 equals PTP. And we thought, okay, we need to gen log the cameras. How can we do that? Yeah, of course, we can use the frame synchronization, run the cameras asynchronously, do the frame sync in the end. But the idea was to try and minimize the glass-to-glass latency as much as possible. Yeah, okay, 5G is already introducing some of the latency, but we thought how far we can really push that. And of course, you can use something like NTP for that, but since we already had PTP, and since this is a research project, we thought, can we really use that? What kind of accuracy we can get? So that's what we've done. Now, of course, we know and love PTP as being a robust and very reliable protocol, except when it's not. And in a very kind of I would say normal condition, it kind of quickly falls apart because it's very vulnerable to asymmetries, especially path asymmetries, because it's a two-way time transfer protocol, but it makes a fundamental assumption that the path from the master clock to your slave clock, or from leader to follower, is the same as the other way around. In reality, it's rarely like that, because networks are living, breathing creatures. Rerouting happens, outages happen, fiber lengths happen. And especially when you're in a wireless situation, you have all those additional things like if my user equipment is moving, if it's changing distance between the base station and the user equipment, I have a Doppler effect. I have network contingency. I have scheduler in the core. So all those things really do not contribute well to the quality of the synchronization. So for static asymmetries, you can address that, but we thought, can we really use that dynamically? And the first experiments we've done without any correction on release 15 network, and we got somewhere in the ballpark of 800 microsecond as an average, and the worst was approximately a millisecond and a half. Okay, that's fine. Like, can we do something about it? Yeah, we can. So we, first thing what we've done, we've measured a static asymmetry. So we basically locked both of our ends to PTP independently, and we did an iPerf measurement. We measured approximately, 150 millisecond or something, and we said, let's compensate for that. And we used static compensation in the client, and we got to approximately 200-something microseconds. But there is a way. The networking industry actually have been doing that for a while. They're much smarter than us. And they said, okay, the PTP version 2, the 2008 and the 2.1 actually introduces transparent clocks that can report through the correction fields the time that the PTP packet is spending inside of the network. So from the time it enters the switch to the time that it leaves the switch. What if we can measure the time that the PTP packet enters the 5G network and leaves the 5G network? And that's what we've done. So the Ericsson URLLC testbed is logged to GPS independently, and it can measure and it can take note of when the packet enters the network and when it leaves on the user side. And it can dynamically report into the correction field. Essentially, the 5G network becomes your transparent clock. So we put together a very kind of extremely simple setup with just a switch and the 5G network and a couple of NVIDIA Mellanox ConnectX cards that can use the PPS output to show the performance of the local oscillator. And we compared on the oscilloscope the PPS output from our clock and from our client. This was the setup. Yes, it's a stationary, so we only measured really the performance of the radio. We didn't measure the effect of the Doppler effect and the moving aspect of it. That's going to be the next steps. And very simple setup on the wired side. So just a standard off-the-shelf NIC, standard off-the-shelf switch, standard grandmaster, and a standard oscilloscope. That's, by the way, the picture of one of the best measurements that we've got. So we went from 800 microseconds to 3 microseconds. And here is Pavlo to tell you more about the actual tests, how we run it, under which conditions. And actually, if you attended the NAB conference, you can download the proceeding where we have in the paper all the kernel tweaks that we've done, all the settings of the clients that we've done, the network settings, the in detail explanation of what the testbed was doing. So please feel free to refer to that. And Pavlo will tell you more about the test now.
Thank you, Ievgen. Those first tests that Ievgen showed were from release 15 network, and as soon as we had a chance to use the new testbed developed by our colleagues from Ericsson that was mostly release 16 with some release 17 features network, the first test we did is just run PTP with nothing helping the PTP, so just as it is. And the results were, as you see here on the slide, so in the middle, this is what we got from the logs from our PTP client, PTP4L. The average accuracy was slightly over 100 microseconds, already much better than on release 15 network. And to compare, we also took the measurements with our oscilloscope, and in those measurements, the average was something like 150 microseconds. This test is actually the best that we did, and it included this functionality that what Ievgen was explaining you about, that turns the 5G network into a transparent clock. We also tweaked PTP client's parameters, and you can find details in the proceedings of our paper. So the results were single-digit microseconds, so something like 3 to 4 microseconds, both in what we've seen in the PTP client logs and on our oscilloscope. That's the graphs of those of the values that the 5G network was putting into correction field of the PTP packets. So basically, that's how long the packets were in transit through the 5G network. In this test, we wanted to see how much the tweaks that we did in the PTP client influenced the accuracy. And well, the difference was not that big, about 10% worse with the tweaks, which just tells us that most important part of it is that transparent clock mechanism, so-called transparent clock mechanism of the 5G network. Another question we asked ourselves was, what if we actually put data on the network, if we will be transporting some video streams? So we generated some load, something like simulated 80 to 90% congestion on the 5G network, and we wanted to see how it will influence the accuracy of the PTP. So we've seen figures, something what you see here, 23, 24 microseconds. It showed us a bit better on the oscilloscope. So it was worse, but not much worse than without the load. So as a conclusion, we've seen that, well, it is possible to use PTP over 5G network, especially if that's like release 16, release 17 network with this functionality. It can go as low as single-digit microseconds. Yeah, that's just to show also our colleagues from Ericsson who couldn't make it here, but who dedicated a lot of effort to those tests. And I guess that is it from us. I thank you very much for your attention, and maybe if there are any questions, we'd be happy to answer.
Thank you very much, Pavlo and Ievgen. So, any questions? I had one question I was curious about. Since you're working with, 5G and related technology, obviously a lot of the phones have GPS receivers in them and things like that. Is there any way to get access to that GPS and use it for your timing references?
Fantastic question. So the project was developing a custom encoder that is based on the off-the-shelf NVIDIA SoC, and potentially, yes, that is a very good idea. It's actually using the GPS receiver in the encoder, but it will be a bit unpredictable in the indoors environment. So for that, maybe something we can test. If the core itself is locked to either a local PTP that is available already in the system from the ST2110, or if it's referenced externally as 3GPP mandates through the GPS receiver, it's possible. So maybe in the future we'll see some sort of a UE with GPS capabilities that will be targeted towards measuring this residential time.